Afternoon, everyone. I'm Shaown from Beijing University of Technology. I'm pleased to display my recent work, Temporal Fidelity Enhancement for Video Action Recognition. Video action recognition has become increasingly critical for several applications such as public safety and assisted driving and as well as industrial monitoring. The video ac- video action recognition's accuracy is very important for support resource optimization. And the temporal attention mechanism helps the help now model to improve the recognition accuracy because attention mechanism help model to learn the key uh, to the informative segments in the video. But this is a common issue that there is temporal infidelity. The temporal the temporal infidelity occurs when temporal attention does not align with the truly informative segments. This infidelity may arise from the training habit, like preferring to continuous segments, even when they lack, even when they lack the um, a semantic relevance. Here are two examples that yeah, respectively from the training dataset and testing set. As we can see, although the green box part match human understanding of the action, but the the red box the red box part have been paid more attention value by those temporal attention models. We believe this temporal attention infidelity is due to two concept issues. First, many temporal attention models implicitly follow the information bottleneck principle. Given a sequence of segment embeddings, these models compute attention and generate video representation by selecting segments with high attention score. Second, the model is usually trained with video labels only, which are too coarse to help me to learn useful segments from the noisy ones. As a result, the model's attention does not necessarily reflect fidelity to the recognition text, but rather lies with the shortcuts learned from the training data. To address this, we propose encouraging the model to disentangle action-relevant and action-irrelevant information from the video segments embedded. Importantly, we aim to achieve this without relying on fine-grained such as segment-level labels. Our strategy introduces a self-adversarial learning framework where the model learns to differentiate between salient and non-salient representations. We train the model to predict action labels using two types of representation in an adversarial way, encouraging it to focus more on truly information and actually critical segments. And we also provide a theoretical support for our approaches, including the theorem in our work. The first theorem proves that our disentangle objective is aligned with the maximum compression principle. That means our objective encourages the model to learn clean and and noisy-free representation that hold fidelity to the action recognition. And the second theorem proves that the previous theoretical objective can be transferred into the practical optimization formulation. enabling effective learning that only need the course that's video level labels. Based on this insight, we propose a novel framework named Temporal Fidelity Enhancement. It consists of three main components. The first one is video encoder. It maps the input sequence of video segment into embeddings. We design this part as a modular, allowing easy integration with state-of-the-art architecture. The second part is temporal disentangler. This module decomposes the embeddings into salient and non-salient in representation using multiple temporal disentangler heads. Each head produces a pair of feature representation capturing semantically distinct information. These are aggregative to form the final representation for downstream action work, action recognition work. Analyze a pair of policymakers. We use two parallel branches, one for salient features and one for non-salient features. Both try to predict action during the training. The salient branches is encouraged to perform well. The non-salient branches is trained adversarially toward capturing repetitive information. The contrast helps the model better distinguish what matters hold fidelity for recognition. And another key of our temporal disentanglement module is the use of our gamble softmax print sampling to generate a pair of adversarial attention maskers rather than a single one. This allows us to explicitly split temporal attention into salient attention masker and non-salient attention masker. These maskers guide the feature decomposition, ensuring that one string capturing high fidelity action relevant information, while the other capturing contextual or noisy information. And we evaluate a method on three benchmark datasets, including long-term action dataset slates and two short-term action dataset, UCF101 and HMDB151. Across all datasets incorporating our TFE framework into existing attention-based models consistently improve performance. Furthermore, we conduct in-depth ablation studies to understand the contribution of each module and validate the theoretical underpinning of our approach. I won't go into detail here, but I'm welcome to read the upcoming paper for a complete discussion. Thank you for your listening.